Hi everyone, welcome back to chemistry. So in this video, I want to talk more about covalent compounds. But we said that covalent compounds happen between two or more nonmetals. So nonmetal plus nonmetal is covalent. And then ionic is usually metal and nonmetal. Polyatomic ions are weird though, because they're composed of two or more atoms that are bonded together covalently, right, sharing electrons, but they have an overall charge, so we call them ions. Remember the prefix poly means many, so more than one atom bonded together with an overall charge. Remember, ion is what we call anything with an overall charge. So you'll notice, right, hydrogen's a nonmetal, nitrogen's a nonmetal, oxygen nonmetal, carbon nonmetal. All of these are bonded together and sharing electrons in covalent bonds, but the ion as a whole has a charge, which means now it can participate in ionic bonding. Sometimes you'll also see polyatomic ions written like this, where they have brackets around the compound, and then the charge on the outside of those brackets. So just so you know that notation exists as well, it's the same idea. It's just to emphasize that it's a polyatomic ion. All right, now I want to switch gears and talk about bond length. So we've noticed after a long time of observing these covalent bonds that as we get more and more covalent bonds, right, we go from single to double to triple covalent bonds, right, we've noticed that the bond length decreases as the number of covalent bonds increases. So as we get more and more covalent bonds forming between two atoms, we see that the bond length gets shorter. And that's because when you've got more electrons, right, triple bonds have 6 electrons being shared between those two atoms. When you have more of those electrons to kind of cushion between those two nuclei, remember in the nucleus of an atom, there's protons and neutrons, but since neutrons have no charge, protons have positive charge, now your nucleus has an overall positive charge. If you have some electrons to kind of cushion that those two nuclei, they can come together closer without being repulsed by each other, right? Because like charges repel. So that's why when you have more and more of these covalent bonds in between these two atoms, the bond length can get shorter and shorter. Really, for our class, I don't need you to memorize what the exact length is of these bonds. I just want you to memorize that single bonds are longer than double bonds, which are longer than triple bonds. All right, so far we've talked about covalent bonds as, electron sharing, the sharing of electrons. But it turns out that these covalent bonds, in these covalent bonds, I should say, electrons are not always shared equally between the two bonded atoms. So for instance, if we look over here at hydrogen bonded to chlorine, this is a covalent bond, right? Two nonmetals, hydrogen and chlorine, sharing electrons. But what we notice when we look at HCl, hydrochloric acid, is that chlorine actually kind of hogs all of those electrons kind of more towards itself. And the reason for that is that chlorine really, really, really wants electrons. It's kind of like if you go out to dinner with a friend and you're like, oh, let's share some fries. But you're sitting there and you're watching as your friend takes more and more fries. Like, well, wait a minute, I thought we were sharing these fries. But your friend's taking all the fries. So you're still sharing the fries, right? But one of you is kind of hogging them. And that's how I like to think of this happening between hydrogen and chlorine, is that chlorine is kind of hogging those electrons in that bond. And what happens is, as chlorine hogs those electrons, and we'll go back to that previous slide in a bit, but as chlorine hogs those electrons toward itself, it kind of pulls all of those electrons to its side, and that results, because electrons are negatively charged, that results in more negative charge on the right side of this molecule, right, by chlorine, than on the left, okay? And you get a molecule that kind of looks more like this, because those electrons are more dense on the right side of the molecule, right? There's more electron density, more electrons are hanging out in that region. Remember, still shared, just shared unequally. And when that happens, we create this kind of difference in charge, or these different poles. Whoops, this shouldn't be there. And we denote that with a couple different types of symbols. So here you'll notice over here we have that negative charge, but it's not a full negative charge, right? Because we're still sharing those electrons. Chlorine hasn't gained any electrons. It's just kind of hogging them close to itself. It's pulling them close to itself. So we actually give it this delta sign in front. That's the Greek letter delta. And it stands for partial. Oops, delta, partial. So it's not a full negative, it's just a partial negative because we're just hogging those electrons, but we didn't steal them. All right, and then, so anytime we have a partial charge, you want to show what that partial charge is, right? So on chlorine, we've got that partial negative, and on hydrogen side, we've got that partial positive. Okay, so you can write that Greek letter delta and then whatever sign that is. Because if chlorine's hogging all those electrons towards itself, hydrogen has less. So hydrogen's got a little bit or a partial positive charge. All right, we can also show this phenomena using these things called dipole arrows. Dipole arrows. And this is, right, dipole, two poles, right? It's showing that difference in charge because we're creating now a polarity between those different sides of the molecule. So on the right side, remember on the side with chlorine, we have that partial negative charge. And the arrow for our dipole arrow points towards the partial negative. So we get that point on the partial negative side. Okay. And then you'll notice on the partial positive side, we get this kind of plus sign. So it's like an arrow with a plus. Okay. And that plus sign always goes on the partial positive side. So I'll put partial positive, partial negative. So those are just two ways that you can show that kind of difference in poles for these bonds. Now, scrolling back up here, so a covalent bond that has an equal sharing of electrons, we give that the name a non-polar covalent bond because we haven't created any difference in poles, right? They're both sharing those electrons equally. And you'll notice here, as an example, we've got hydrogen bonded to itself. Anything bonded to itself is not going to create this kind of difference in sharing or this unequal sharing because both of those atoms want electrons the same amount. So hydrogen is bonding with another hydrogen and they both want electrons the same. It's like they're splitting fries and they both were like, yeah, I want 5 fries. And the other person's like, so do I. And then they share equally. Which is different, right, from a polar covalent bond, where we're creating that difference in poles because chlorine wants electrons more. So it's going to kind of pull them towards itself. All right, now we can actually judge kind of the relative polarity of these covalent bonds using something called electronegativity, which is a measure of how strongly an atom attracts electrons when it forms a covalent bond. So what we can do is we can say, okay, I know which two atoms are bonding together in this covalent bond, sharing electrons, but I want to know which atom, if any, is going to pull those electrons towards itself more, creating that kind of polar, those difference in poles, or that polarity, because that's going to dictate how those molecules behave in nature, whether they're polar or not polar, and we'll talk about that in the future. All right, so it turns out chemists have kind of compiled some information about the electronegativity values for these different elements, and they use an electronegativity periodic table or an electronegativity scale, also known as the Pauling scale. And this shows the relative electronegativity values for these different atoms. So how much do these different atoms want electrons, and how much are they going to hog electrons in bonds? So what we've noticed over time is that as we go right and up on the periodic table, our electronegativity, or En, is increasing. So as we go right and up. You could also write that as like kind of averaging those two arrows out as a diagonal arrow, right? En increases. So something like fluorine, for instance, you'll notice its electronegativity value is 4.0. versus something like francium down here, which is 0.7. So very different attraction of electrons for fluorine versus francium, right? Fluorine really, really wants electrons, so it's going to kind of pull them closer to itself in any time it's kind of bonding with other things in these covalent bonds. All right, so for our purposes, you're never going to be asked to memorize or know off the top of your head some kind of electronegativity value. Like, you're not going to need to memorize that fluorine has a 4.0 electronegativity value. If you're ever asked to calculate electronegativity differences, and we'll talk about that in a little bit, you'll be given the electronegativity values. So don't memorize this. What I do want you to memorize is just that generally, as we go right and up on the periodic table or diagonal to the right, our electronegativity for these different atoms is increasing. That's the trend that we see in nature. But what if we wanted to kind of quantify this a little bit better? So looking over here on the left for a second, you'll notice we have some different type of bonds that we're familiar with, right? We've got pure covalent, which is just, a regular covalent compound, some bond, something that's sharing electrons equally. And then we've got the polar covalent, which is sharing electrons unequally. And then we've got ionic, which is transferring electrons. Right? No longer sharing, right? Something's giving electrons and something's taking electrons. So I actually, this is cool, but I actually like to think of this as a scale or as a spectrum, where on one side, on the left, you've got, pure covalent. And on the right, kind of the opposite, is ionic, right? In pure covalent compounds, we are sharing those electrons completely equally. In ionic compounds, something is giving them and something is taking them. And then kind of right in the middle is something like polar covalent, where, yeah, okay, we've agreed to share, but one atom is kind of not sharing very well. And that's resulting in that polarity. All right, so how do we actually quantify this numerically? So just to have a more specific way of defining what type of bond we have between particular atoms, we can do that with our electronegativity values. So when you look at the periodic table up here, we have this electronegativity periodic table. And you can just Google this online if you're ever curious. But we have our values here. And the idea with figuring out these bond types is we can quantify, okay, if the difference in electronegativity between our two atoms is less than 0.4, we can call that type of bond pure covalent. If it's greater than 1.8, we can call that ionic, right? Then we're looking at an electronegativity difference that's large. And it's so large, in fact, that we can't really call it, they're not sharing anymore at that point, right? Someone's giving and taking. And then anything in the middle of those two, right? Between 0.4 and 1.8 is going to be pure covalent. So let's try this out with some examples, and we'll do these together first. So we've got hydrogen and fluorine. So first what I want to do is I want to look at these two on my electronegativity chart, and I want to see, all right, what are their electronegativity values? So for hydrogen, we've got an electronegativity value of 2.1, and what was the other one? And for fluorine, we've got an electronegativity value of 4.0. So 4.0 and 2.1. So 2.1 and 4.0. So in order to get the difference between those two electronegativity values, we're just going to subtract those numbers. So I'm going to take 4.0 minus 2.1, and I'm just going to get the difference between those two. And you shouldn't get a negative number. Always just subtract. We're just looking for the difference. So always subtract the smaller number from the larger number. So we're going to get a difference of 1.9. which is, let's see, is that going to make our compound pure covalent, polar covalent, or ionic? Well, let's go up to our chart here. It looks like ionic is categorized as anything or defined as anything that's greater than 1.8. So our compound here, HF, would be considered ionic. All right. What about chlorine bonded to itself, 2 Cls? So let me just draw this out for you. This is going to look like this. Chlorine bonded to chlorine, right? That's the Lewis structure for chlorine. Now, before we do anything, what do you think? Is this going to be pure covalent or non-polar covalent? Or is it going to be polar covalent, or is it going to be ionic? It's going to be non-polar covalent, and I can tell just by looking at it. And the reason for that is that it's bonded to itself, right? So in terms of how many fries each of these chlorine atom wants, they want the same number of fries, right? So they're going to share equally. So I guess let's just do the calculation though, just to be super safe and just to show you what I mean. So chlorine's over here, and it has a 3.0 electronegativity difference. So mathematically, right, 3.0 minus 3.0 is going to give us no difference, which means this is non-polar covalent. I tend to kind of call this non-polar covalent rather than pure covalent. That's just because that's the way I learned it, was calling them non-polar. But you can call it pure covalent. I'll still know what you mean. All right, now lithium and chlorine. Let's check. So lithium is 1.0, and chlorine has an electronegativity value of 3.0. So that's going to give us 3.0 minus 1.0, which gives us 2, which again, I'm noticing, right? That's higher than even 1.9. So that one's going to give us an ionic compound. And this actually makes sense, right? Because I said, remember, ionic compounds are between metals and non-metals. Lithium's a metal and chlorine's a non-metal. So we would expect it to be ionic. And it is. All right, so practice this one again, and let's just see what we think. So for N2, what do we think? Pure covalent, polar covalent, or ionic? Yeah, pure covalent for this one. Why? Yeah, it's bonded to itself, right? Anything bonded to itself is going to be sharing those electrons equally, and it's going to be covalent. All right, what about CO, carbon monoxide? Well, first off, 2 nonmetals, right? So we're already kind of assuming covalent. We could have done the same thing here, right? But is it polar or nonpolar? Well, let's think about it. So carbon, all the way up here now, is an electronegativity value of 2.5, and oxygen is 3.5. All right, so 3.5 minus 2.5 is going to give us 1.0, which is going to give us, let's look at our chart here. Well, 1.0 is right in the middle here. So that's going to be polar covalent. So sharing electrons, but sharing them unequally. Polar covalent. I don't know why I switched to blue here, but that's okay. All right, and then magnesium and oxygen. Looking at this, right? Oxygen, non-metal. Magnesium, what's magnesium? Yeah, metal. So I'm already kind of thinking, well, it's probably going to be ionic, but let's just double check. All right, so oxygen has a 3.5 electronegativity value, we said, and magnesium has a 1.2. So that's going to give us a 2.3 electronegativity difference, which that's pretty high. Let's just double check though with our chart. Yeah, 2.3 is way greater than 1.8, so that's definitely going to be ionic, which checks out, right? Non-metal plus a metal. All right, and then the very last thing for this video is I want to talk about something called molecular mass. And this is very, very similar to formula mass, which we talked about in our ionic bonding chapter. It's so similar, in fact, that it's pretty much the same thing. It's just calculating the mass of a molecule rather than an ionic formula. So before we said, okay, sometimes we want to know, all right, what's, the mass of something like NaCl, right? And we said, all right, well, we have one sodium atom, which is going to weigh, whatever its atomic mass is on the periodic table. And then we've got one chlorine atom, right? And then you're going to just add those two masses together. This is the same thing now. We're just talking about a molecule, right? A covalently bonded compound. But it's the same idea. If we want to find the molecular mass of something like methane, CH4, we can say, all right, well, I have one carbon, and that carbon atom is 12.011 AMU in weight, and I can look that up on the periodic table, right? The atomic mass. And then I've got 4 hydrogens, which each have a mass of 1.008 AMU. And you might get slightly different numbers from me here, and that's okay. That's just because you might be looking at a different periodic table. So a little bit of variance is all right. And now we have to total up those numbers. So remember your PEMDAS rules. You got to multiply that first. So 4 times 1.008 is 4.032 AMU. Okay, and then we want to add up these two numbers, right? Because we want to get the mass of the entire molecule of CH4. So let's see, 4.032 plus 12.011 is going to give us 16.043 AMU. Right, so I don't want to spend a ton of time on molecular mass because it's very, very similar to formula mass. In fact, it's the same. It's just now we're calculating the mass of a molecule rather than an ionic compound. But if you have any questions, as always, feel free to let me know. And I will see you in the next video for chapter 5.